Hello and welcome to the logic of it all. In this video, we are going to look at three more logical connectives: negation, implication, and if and only if. Let's start with negation. So we have this proposition P. Its negation, which we write like this, and we read that as not P, is a new proposition, and as we said before, it's a compound proposition because it contains a simpler proposition, namely P itself. So for example, if P is the sentence that says Huddersfield is the capital of England, its negation, not P, will be the sentence that negates P, which means it says Huddersfield is not the capital of England. Now, in terms of when or not P is true or false, similar to the previous connectives, it depends on the truth value of P. But here, since there is only one proposition involved, it's just P, there is no P and Q, there are only two possibilities. It's either that P is true or false, which means our truth table is going to have only two rows. And again, as you can expect, the truth value of the negation of P is going to be always the opposite of the truth value of P. In other words, in the first case where P is true, not P is going to be false. And in the second case, when P is false, not P is going to be true. So the truth table of the negation is very simple. It has only two rows, and its truth value is always the opposite of P. Now here's an example. You have two propositions P and Q. P says 2 plus 4 equals 7. Q says 12 is a multiple of 4. So the first compound proposition that we want to evaluate is not P and Q. Now the first thing to note here is that when we write like a proposition like this, the negation has precedence over conjunction, which means that this means not P and Q. In other words, the negation is only applied to P. Okay? Now, to be able to evaluate this, we need to know the truth value of P and Q. P says 2 plus 4 equals 7. Obviously, that's false. Q says 12 is a multiple of 4, which is true. Okay? So if we substitute here, P is false, so its negation is going to be true, and Q is also true. And based on the truth table for conjunction, true and true is true. So that's the first one. The second example is P or not Q. Again, what this means is we negate Q and then take the disjunction of that with P. Now we know that P is false, so this is false, and we know that Q is true, which means that not Q, its negation, is going to be the opposite, which is false. So we have false or false, and again, based on the truth table for our connective, which is disjunction in this case, we know that false or false is false. And finally, we have not P and Q. Now, before evaluating this, I want you to pay attention to the difference between the first and the third proposition. So in the first proposition, we are only negating P, so it's not P and Q. So we are taking the negation of P and then combining that with Q with and, with conjunction. But in this third example, we are combining P and Q using and then taking the negation of the entire thing. So this is a different proposition. The third proposition is different from the first one. Now, given that, let's go ahead and evaluate this. So we know that P is false, and we know that Q is true. So false and true, and then the negation of that. Now, again, based on the definition of conjunction, we know that false and true is false. So we are taking the negation of false, which is true. So there you have it. Now, the second connective we are investigating in this video is implication. And you have seen implication under the name conditional statement as well, and it's used in programming languages. So it's basically is your if-then situation. So we have two propositions P and Q, and then their implication, which is denoted like this, is representing this one represents if P then Q. Now it's useful to have some terminology here, and you can see these in textbooks and lectures, and we are going to use these terms later on in later videos. And that is when you have an implication if P then Q, then P is sometimes called the hypothesis or the premise of the implication, and Q is called the conclusion of the implication. Okay, so the left side is a hypothesis or premise, the right side is conclusion in an implication. Now here's an example. P is the proposition 2 plus 2 equals 5, which is obviously false. And Q is Samuel Beckett was an Irish novelist. Now I leave that to you to figure out whether that's true or false, if you don't know Samuel Beckett, which you should. Now, the implication created with P and Q, which is written like this, will represent the sentence that says if 2 plus 2 equals 5, then Samuel Beckett was an Irish novelist. Now, the reason that I've chosen this example is that when we talk about implication, if this is your first time seeing this in logic, you may assume that there should be some type of relationship between P and Q. Or sometimes people think that P must be the cause of Q. P must be the reason that Q happens. So if you do this, then that happens, or something like that. But in logic, implication doesn't necessarily have anything to do with causality, right? And that's why I've chosen these two statements or these two propositions P and Q to be completely irrelevant to each other, to show you that in logic there is no need for P and Q to be related to each other in any way, and we can always create an implication with two propositions. Now the next step is obviously when is if P then Q true and when is it false, right? So again, since we have two propositions involved, P and Q, there are four possibilities. It's either that they're both false, P is true, Q is false. Third possibility, P is false, Q is true, and it could be that they're both false, right? So similar to conjunction and disjunction. Now we know what this means, right? This means that if we draw the truth table for the implication, we are going to end up with 4 rows, one for each one of these possibilities. Now, the first case says, if true, then true. So the premise is true, the conclusion is true, and it's intuitive that, the implication must be true in this case. The second case is also intuitive. If your premise is true, but your conclusion is false, then the implication is false, right? Now, the third one and also the fourth one are the ones that, if this is your first time seeing implication in logic, it's a little bit counterintuitive. So both of them say we can combine the third and the fourth row into one sentence, and that is, if the premise is false in an implication, it doesn't matter whether the conclusion is true or false, your implication is going to be true. So if you have false, if false then anything, then that whole thing will be true. It doesn't matter whether your conclusion is true or false. So from a false premise, you can conclude anything, basically. Okay? Another way to think about this is that an implication, if P then Q, is false only in one case. And that one case is where the premise is true, but the conclusion is false. So that's another way to think about this. Now, as I said, this is a little bit counterintuitive, and if you're interested, you can look this up. There are some logicians and some mathematicians who look at implication differently. Okay, so if you look up intuitionistic logic or constructive mathematics, you can take a look at that, right? But for the majority of mathematicians, they follow these rules, which is called the classical logic. Now, here's our final connective in this video, if and only if. So you see the arrow is now goes in both directions. So we read this as P if and only if Q. And basically this is just a shorthand for if P then Q and if Q then P. So P implies Q and Q implies P. And we can draw the truth table for this. Again, you can see that we have 4 rows because it's either that P and Q are both true, P is true and Q is false, P is false and Q is true, and finally they're both false. So we have 4 rows, one for each one of these potential cases. Now what we need to do is we need to compute the truth value of if P then Q. We know how to do this using the previous slide. Then we need the truth value of if Q then P. We know how to do that again using the previous slide. And now when we have this, we use what we know about conjunction. So true and true is true, false and true is false, true and false is false, and finally true and true is true. And because P if and only if Q is defined this way, then we can compute its truth value as the final call. Now, again, if you want to remember this, you can think of it this way. P if and only if Q is true, exactly when P and Q have the same truth value. So if they're both true or they're both false, then their if and only if is true. But if they have different values, like one is true and the other one is false, then their if and only if is going to end up being false.